Okay, so today's like in this occasion, I would like to continue our topics on magnetic fields, where magnetic fields itself is a consequence of current that is flowing inside of wire, right? So in the previous lecture, we learned about how current and also voltage behave inside of a circuit. But now we move on to the effect current that flowed inside of wires, metallic wires that produce another effect that called as magnetic fields. And the way we learn about magnetic fields is actually similar with how we learn about Coulomb's law in electric fields, where we learn about the forces first and then deals in depth on the following week or in next weeks about how we compute the magnetic field itself. So the first part of our discussion on magnetic fields is to learn about the effect of magnetic fields on particles, charged particles, and also current that flow through wire. And then in the following week, we learn about how the creation or the generation of the magnetic field itself inside of a current wire. And as I mentioned in Thursday lecture, again, today is not going to be a compulsory lecture. So if you have other activities or you have plans to do recreational stuff, please do so, because officially we have holiday today. So the one that we going to learn at this point is just to have a preliminary view on how magnetic fields affect on charged particles and charged particle particularly, because in Thursday we still have Thursday to discuss about more on magnetic forces. But what I'm going to show you today is things that are related to effects of magnetic fields to moving charged particles. Okay, so the key idea here, I'm using the textbook for today's lecture. Besides, I also prepared the slides that is related to today's topic, but I just want to deal more with this textbook because the information about the matter is present here basically. And the key ideas of today's lecture is about when a charged particle moves through a magnetic field B. Okay, so in this case, magnetic field have a different variable being used here. If we remember the previous lecture on on electric fields, we use capital E, and then we have an arrow above it that tells us about fields quantity is basically a vector quantity. It has value, value means here is the magnitude and also directions. For magnetic fields, we have capital B letter and arrow that tells us that magnetic fields also a vector variable. It has magnitude and also directions. Okay, so when a charged particle moves through a magnetic field B, a magnetic force will be produced that acts on the particle, and the relation or the behavior will be following the equation. So as we learn about this later, becomes the Lorentz Force equation that tells us about how F here is the magnetic force produced when a moving charged particle interacting with external magnetic fields. So again, in today's lecture, we're not going to learn how B is created, okay? Not at this point, because the creation of B will be discussed later on. But we learn about how B interacting with a moving charged particle, and it will produce magnetic fields. Okay, Q here is the particle charge. So if we consider a positive charge, such as anions or H plus ion, we need to place the signs here as a positive. If we consider an electron or a negative ion such as OH minus, okay, and then usually OH minus has a -1 signs, then we need also to put minus signs over here. So the direction of B will depend on the sign of B and also the sign of the direction of the moving particle. And V here is the velocity of the particles. Again, in electromagnetism, the effect of magnetic field to a charged particle usually happens when the particle is moving. If it's at rest or if it's not moving, then there will be no magnetic force on the charged particle. So therefore, later on, we will learn also a moving particle such as electrical current inside of a wire can also influenced by the magnetic field and creating magnetic forces inside of them, or when a certain wire interacting with other wire. But there will be another discussion, but we will focusing more on this equation instead and how this phenomena is occur. Okay, and then the second topic that we are going to cover in this short lecture is the right-hand rule for cross product, because we have here in this equation a multiplication operation, but not in dot signs, but it has a cross sign where this type operation will produce another factor that will be perpendicular 90 degrees from each other. So we need to have the direction of B, direction of particle velocity. It needs to be not parallel. It needs to be have different direction. And the two directions will produce forces, okay, will produce magnetic force that 90 degrees or perpendicular to V, to the velocity, and also to the magnetic field directions. So in order to describe the direction easily, we introduce a right-hand rule for cross-product multiplication that gives the direction of cross product of velocity and magnetic fields. The sign of Q. Let me see. Oh, okay. The sign of the particle, the sign of the particle motion, or the sign of the particles charge, then determines whether the magnetic field is in the same direction as the product of phi cross B or in the opposite directions. Okay, so we will learn about that later on. Okay, let me, oops, sorry. Okay, so what is the physics in the that we're talking about today? So after we have discussed one major goal of physics is the study of how electric field can produce an electric force of a charged object. A closely related goal is the study of how magnetic field can produce magnetic force on a moving charged particle. In the lecture of electric field, we usually consider that the charged particles that we observe can be in electrostatic condition. The charged particle itself or the charged or the charged object itself is not moving, okay, but it certain position will produce some kind of a field or some kind of an influence surrounds it, and then the interaction between that one particular charged particle with another charged particle will creates electric forces, and one charged particle will produce fields around it, and then when it's interacting with other particle, it produces force. But now, the charged particle that we consider in electric field, oh, sorry, in magnetic field, are in the condition where it is moving, okay? So if we have a condition where a charged particle is not moving or at rest or in some kind of a static condition, it is not moving. So if we influence or if we give an external magnetic field to the particle that is not moving, then there will be no force acting on the charged particle itself. So there will be no acceleration per se, because force usually correspond to mass times acceleration. So there will be no change in motion. There will be no chance of that resting particle be able to move to other position, because the formula given here, the condition is that force that is produced due to external magnetic fields need to influence a certain charged particle that in moving condition. Okay, so you may already have a hint of what magnetic field is if you have ever attached a note to a refrigerator door with a small magnet, okay, or accidentally erase credit card, or accidentally erase a credit card by moving it near a magnet. The magnet acts on the door or the credit card via its magnetic field. The application of magnetic fields and magnetic forces are countless and changing rapidly every year. The usage or the application of Wi-Fi signals is another type of magnetic fields application in our daily life. Here are just a few examples of application of magnetic fields. So for decades, the entertainment industry depended on the magnetic recording of music and image. Oops, sorry. Okay, so if we have cassettes or if we have that we use in our computer or inside of our cell phones, the working principle of the equipment is basically using the application of magnetic fields to a certain metal, so that partition inside of the hard disk or partition inside of a cassette can maintain a certain information due to electromagnetic print inside of the metal, inside of the material, and how we print information inside of a partition metals or a partition material. It needs to be a magnetic field influence, okay, a magnetic field external influence to that material. And the magnetic field influence usually produced by some kind of electrical devices that we use to generate signals, and the signal is safe, containing information, whether it's sound, whether it's in text, whether it's in visuals, colors, etc., and so on. So in the beginning, so in the early 20th century, we use electric field for recordings using magnetic recording of music and images of audio tape and videotape. Although digital technology has already replaced magnetic recording, the industry still depends on the magnet that controls CD and DVD players and computer hard drives. Magnets also drive the speaker ones in phones. So whenever we have earphones and headphones, when we listening to lectures, listening to dramas, listening to music, listening to any sort of type of entertainment, for example, we use the application of magnetic fields that produce motion inside the earphone, so that it will produce voice or vibration that match with the frequency of sounds that we receive in our ear. Modern car comes with dozens of magnets because they are required in the motor for engine ignition, automatic window control, sunroof control, and windshield wiper control. Most security alarm system, doorbells, and automatic door latches employ magnets. In short, you are surrounded by magnets. Another example that we usually see is for using electromagnetic to collect or transport scrap metals in steel mill, or we sometimes saw this in television when a certain factory needs to move a metallic material from cars or from trains to the production factory usually, and they use magnet in order to move it from the car to the factory. Yeah, and in this case, in the textbook, we see an application of this, an electromagnetic metal that is a huge cylindrical metal here will be electrified, will be connected to a certain electrical, so that there will be currents, electrical currents flow through this metal, and the production, and then the current itself will produce magnetic fields that will attract, okay, that will attract magnetic materials here, okay, magnetic material here, where the magnetic material here, for example, metals or a metal powder or metal scraps like this one, has electrical charges on the outskirts or in the skin of the body. So therefore, we could attract these metals using the magnetic field produced in the cylindrical steel or in the cylindrical metals like this one. The science of magnetic fields is physics, and therefore the application of magnetic fields is engineering. Both the science and application begin with the question, what produces a magnetic field? Okay, what produces magnetic fields? In this case, is basically due to the flowing of currents inside of metallic bodies. and the metallic bodies can be wires that we usually saw in electrical circuit, or as you can see here in the factory, it can be also employed or applied into a body of metals. Okay, the body, this cylindrical body of metal is electrically charged by the flowing of current, and then it will produce magnetic field, and the magnetic field itself will attract another metals, another charged particle, and therefore we have attracting forces between the metal, the cylindrical metal on top, and then the particles of dust and scraps metal beneath it. Okay. Okay. Because an electric field is produced by electric charge, we might reason or we might expect that magnetic field B is produced by magnetic charge. Okay. Although individual magnetic charges, such as magnetic monopoles, are predicted by certain theory, their resistance has not been firm. Okay. So initially, we think that since electric field E is produced by electric charge, so that B is also produced by magnetic charge. But this is not the case. Okay. But this is not the case. How then magnetic fields produced? There are two ways. Okay. One way is to use moving electrically charged particle, such as a current in a wire, to make an electromagnet. And then the other way to produce a magnetic field is by means of elementary particles such as electrons, because these particles have an intrinsic magnetic field around them. The one that we learned today is more on the first way, or the first description. Okay, the first description on how magnetic fields is produced, because if we deal more on the second mechanism, we need to have knowledge on modern physics topic, but we haven't got into that point yet. So therefore, we will learn more about how magnetic field is produced due to moving current inside of a metallic body or inside of a wire. So our first job in this chapter is to define the magnetic fields B, and we do so by using the experimental fact that even that when a charged particle moves through a magnetic field, a magnetic force B acts on particle. Okay. In the lecture notes, the definition of B, or the definition of magnetic field magnitude, or the value of magnetic fields, we can define magnetic field B to a vector quantity that exists when it exerts a force FB on a charge moving with a charge moving with velocity V. We can next measure the magnitude FB when V is directed perpendicular to that force, then define the magnitude B in terms of the force magnitude. In this case, we are given with the formula B equal to FB divided by Q times V, like this one, where Q is the charge of the particle. Again, Q has signs that depends on whether the charged particle itself is a positive particle or a positive ions, etc., and so on, or is a negative one. We can summarize all this result with the following factor equation that we already see in the previous description. That is, the force FB on the particle by field B is equal to the charge Q times the cross product of its velocity V and the field B, all measured in the same reference frame. We can write the magnitude FB equals to the value of Q the value of the electrical current, or not the electrical current, but the charged particles times the velocity. So it means that the magnitude of Q here, if you saw a mathematical equation that has this type of sign, this type of operation, well, it has two bars in the right and the left. It means that we don't need to consider whether it is positive or negative. We just need to consider the value or the magnitude only, because here we just need to find the magnitude of the force itself. Okay, so the magnitude of the force itself is equal to the magnitude of the charged particle of the Q, regardless the signs of the particles, and then the value of the velocity, or we call them as the particle speed, and then the value of B, and then the direction. Okay, the direction between B and V. So B and V will not be always perpendicular to each other. It can have a certain angles between the two of them, but it must not be parallel. Okay, so the direction of moving velocity, okay, the particle's velocity, and the magnetic field, the external magnetic field that influencing the particles, must not parallel to each other. So the phi, or the angle here, must not equal to 0 degrees, or in other words, the direction of V and B must not be the same. Even if the direction has a small angle, the sign of that small angle still produce a certain value. It will not be 0. Okay, so if sign of the angle between V and B is equal to 0, then we will not get any magnetic fields. So if a particle, if a moving particle is being influenced by B, and the direction between the moving particle and the external B itself has angles, then we should produce, or there should be magnetic fields that is produced from the interactions. Okay. For illustration, actually, how B, Q, and V is behaving, or how does this produce, or how this is the case, is when we look at this example. Okay, taken from example 1, talking about magnetic forces on particle, on charged particle. We consider here in the example a proton in a particle accelerator has a speed of 5 times 10 to the power of 6 meter per second. The proton encounters a magnetic field whose magnitude is 0.4 Tesla. Okay, so Tesla, the car brand, the electric car brand that we usually hear in the news, or in videos, or in social media, or any type of media, is usually is basically the same. Is basically the same name of units that magnitude of the magnetic field has. So the unit of magnetic fields is Tesla, the same name that car manufacturer use, because one of the pioneer who learned about magnetic fields is basically Nikola Tesla, the one who inspired Elon Musk to produce its cars. Okay, so we have a charged particle. So let me use the illustration here. So we have a charged particle here, the yellow one, and then it moves with certain velocity. So remember in mechanics, remember in elementary physics 1, when we learn about mechanics, or kinematics to be precise, a certain object has when a certain object has velocity, the velocity itself has directions. It has a tendency to go to some direction or to some locations, pointing to some locations. So there is some kind of a direction dependency on the velocity. So if we talk about velocity, or we talk about how the orientation of a moving body, it should have certain direction. So in this case, we have a charged moving particle with velocity and the direction of it, and also its direction known this point, and then the moving particle is now influenced by an external magnetic field, which magnitude is equal to 0.4. Okay, so the rest of the problem here, whose direction makes an angle of 30 degrees with respect to the proton velocity. So see part C of the figure like this. So in this case, in this case, the direction of the particle has 30 degrees difference with the direction of B. So find a magnitude and direction of the force of the proton, okay, the magnitude and direction of the magnetic force, to be precise, that is happening at the protons, and the acceleration of the protons. What will be the force and acceleration of the particle if the proton replaced by an electron? So it has a similar type of particle, but different signs. Okay, so the first illustration that we use in the figure, okay, first of all, we consider a velocity that has same direction with B. Okay, again, if we use this formula, okay, if we use this formula, which later on we will call this as a Coulomb's law formula, sorry, not Coulomb's law formula, but Lorentz law formula that relates the magnetic force F with B and also V, okay, which origin is basically comes from here. We see that whenever V and B has direction and same, okay, has the same direction, like in this case, in the first case, then the magnetic field produced at the particle is equal to 0. Okay, because the direction of V and B is the same. What about if we have this type of motion when the charged particle now move to the right, when the charge moving particle move to the left, sorry, yeah, moving to the left, and the external magnetic force is pointing to the right directions. So one is moving to the left, but the external magnetic field goes toward the right direction. In this case, the magnetic field produced in the charged particle is also 0. Okay, because even though it's 180 degrees difference with the first situation, but the planes of where the direction of V and B, it's still the same. Okay, so even though this one has 180-degree opposite direction with B, but it is on still on the same plane, which is basically the x-axis. So even though this one is moving to the left, and then this one, the external field itself is directed toward right location or right directions, but the interaction of V with external B here is still producing 0 magnetic fields. Okay, because V and B itself is still on the same plane. Okay, it's still on the same on the same orientation, even though the velocity is 180 degrees to the direction of B. So therefore, the result of phi cross or phi multiplied with B using a cross product here for a case where charged particle moving to the left where external magnetic field moving to the right will produce zero magnetic field. Okay. Now we have an extreme case where the direction of V is 90 degrees. Okay. So if we have a condition or a problem where V and B is entirely perpendicular to each other, then in this case, we will have a maximum production of magnetic force, because from here, the sign of theta or the sign of phi that we used in the previous slides tells us about the direction or the difference of direction between B and V. So since the sign of theta equal to 1 produced by a 90-degree orientation, it means that, and since the maximum value of sine of certain angle is equal to 1, it means that the produced magnetic fields from this type of interaction will be maximum. Okay, will be maximum. So if we have this type of problem, or if we have this type of condition where V and B direction is 90 degree, then we will have a maximum value of the magnetic field. And also we could have magnetic field from this type of scenario, and in this type of problem. Okay, so since the initial problem that we saw here, the direction between V and B is 30 degrees, then the illustration can be done in the third figure, like this one. So we have V that moving towards here and B move to the right. In this case, since V and B is not parallel, it is not on the same plane, or sorry, it is still on the same plane but has different direction, or it is not the same orientation with B. So magnetic fields in this case will also produced. Okay, we can also have magnetic field for this type of settings. So if we have, so again, if we have V and B in the same direction or 100-degree direction, like the first problem in figure A here, we will get zero magnetic field. If we have V and B totally perpendicular to each other, we will have a maximum we will have a maximum magnetic force like this one. But if we have smaller angle, okay, not 90 degrees, but it still has angle, so that B and V have different direction, magnetic field will be produced. Okay, now, the first question is to find the magnitude and direction of the force on the proton, since we have B, V, and F. So why does the magnetic field F is behaving upward or moving toward upward condition or upward direction is due to the fact that in this case we apply the right hand rule, or the first right hand rule. Okay, so in this case, whenever we have V and B, there should be an F that pointing towards up if we have this type of problem. So extend the right hand. Okay, so right hand rule number 1 tells that if we have a problem where a charge moving particle is influenced by external magnetic field, there should be a magnetic force that pointing perpendicularly to the V and B direction. And if the orientation is known, then the orientation of F will follow the right-hand rule principles. Okay, the right-hand rule number 1 principle. So if we extend the right hand, so the finger point along the direction of the magnetic fields, and the thumbs face in the direction of the magnetic force that act on the positive charge. If the moving charge is negative, the direction of the force is the opposite to that predicted by right-hand rule number 1. So in this case, in order for us to solve the direction of the magnetic force, we can use our thumb as the direction of particle velocity or the particle motion, and then our index finger for the direction of the external magnetic field, and then the inside of our palm will be the direction of the F or the magnetic field. If the charged particle that we use is a negative one, such as electron, then the direction of F becomes downward. Okay, if it's positive, it moving out is moving upward. Okay, moving to the up position, or it is in the inside of our palm. But if it's negative, then we use the outside of our palm. Okay, in this case, moving on to the solution of the problem, find the magnitude and direction of the force. The magnitude of the force, we could use F equal to the magnitude of Q times V times B times sine of theta. From this computation, we could have the force is 1.6 times 10 to the power of minus 13 Newton. And the direction that is shown in this figure is moving to the upward locations. Okay, it's moving upward. Again, if the problem states some directions, okay, so if a certain problem that we face later on gave us another directions, then we need to apply our right-hand rule to the problem that is being asked at that point. So in the illustration that we have here, this is just a simplistic model or a simplistic illustration where B is pointing to the right, whereas the velocity is moving with a certain direction to B, or in this case is moving to the 90 degrees to the right of B. Where in exams or in assignment or in student assignment, the direction of B and V can differ. Okay, can has different direction. So therefore, we need to move our hand, but still using the same principle where the thumb is the direction of V, and then the index finger is pointing to the magnetic field direction, whereas our inside of palm is the direction of magnetic force. But this is true for a positive for a positive sign particle, where the outside is going to be more relevant to the negative one. Okay, the second question is to find the acceleration of the proton. So the acceleration of a proton can be computed using Newton's equation. Okay, where we knew the amount of force from the magnetic field. So we now knew about the value of the magnetic force, and the same force is now being applied to to move with different directions. So in order to change the velocity or change the direction of the velocity, we need to have acceleration. So to find acceleration, we use FMA that we learned in physics 1. So the acceleration is equal to 1.6 times 10 to the power of minus 13 Newton divided by 1.67 times 10 to the power of minus 27. So this is basically the mass of the proton itself. So the division of the two quantities here will produce a value of 9.6 times 10 to the power of 13 meter per second square. So the acceleration has a high rate of or a high magnitude of acceleration, and the direction of acceleration itself will be the same direction with the force. Okay, so when a moving particle interacting with external magnetic field, it produces magnetic force. The direction of the acceleration of that magnetic force is the same direction with the F. Okay, so since the F in this case is pointing upward, then the acceleration also pointing upward. So we can see here. So we can see here in this case that eventually this moving particle, when it has initial direction pointing this way or 30 degrees to 30 degrees to the direction of B, now is being brought up, okay, is being pulled up to the upward condition. So later on, we will see a condition or a situation, okay, like this one, okay, where the initially moving particle toward a certain direction will be brought up. Okay, we take the particle into upward direction, but since the magnetic field itself will be influencing at all time, the direction of F will be changing throughout time. Okay, so later on we will see a condition where we will see a rotation of motion, okay, rotation of motion that is acting on the charged particle due to the influence of magnetic fields B that is represented by this crosses here with the moving particle. So moving particle influenced by the external magnetic field, and it will produce acceleration upward. And at this point, the acceleration becomes leftward, and then after that, it moves again to the top, and then at this point, the acceleration goes down, and then at this position, the acceleration moves to the right, and so on. So it will create a rotational motion at this charged particle. So this is the effect of external magnetic field to a moving charged particle, which is positive. If it's negative, then the motion will be a rotation, but goes to the bottom, to the downward locations. Okay, continuing the problem. Okay, continuing in solving the problem of example 1. What would be the net force and acceleration of the particle if we replace the proton with an electron? Okay, so in this case, when we change the proton with an electron, the mass of the electron is practically the same with the mass of proton, isn't it? Yeah. Oh, sorry. The mass of the proton. Sorry. The charge of the electron is the same with the charge of protons, but the mass is smaller. Okay. I revise the statement that I made. the mass of the electron is much smaller compared to the proton, but the charge of the electron is the same. So therefore, since the charge of an electron has the same magnitude with protons, the magnitude of the magnetic force will be the same, but the direction will be the opposite direction with the proton case. In the proton case, we will have a force pointing upward. If we replace this with electron, the force will act downward. But what about the acceleration? The acceleration, again, will be replaced by the mass of the electron, and the mass of electron itself is smaller compared to the mass of proton. So therefore, since the mass of electron is smaller, then we will have a increase of velocity, increase of acceleration that is generated at the electrons. Okay, so the value of acceleration of that electron will be higher compared to the acceleration of the proton. Okay, so how we illustrate this using the right-hand rule over here, and the formula that is given here. And this is the Lorentz law formula in vector form, whereas here is the Lorentz law formula in scalar form. Okay, if we want to solve the problem using scalar form, we just need to use the right-hand rule to define or to describe the direction of the magnetic force. But if we use the vector form like this one, we don't need to define it using the right-hand rule, because the cross product itself is already include the principles of the right-hand rule. Okay, if you have problems for this applications later on in Thursday lecture, we could talk more on this matter. Okay, so here I will present you the difference. Okay, the differences between the influence of external magnetic force with respect to the influence of external electric field. So if we have a charged particle that is moving like this one, so if it's moving from here to here, and then the magnetic field and then the electric field, okay, if we have a parallel plate that produce electric field uniform like this one, so whenever this particle move inside of this parallel plate, the motion will be on the same direction with E, because in the previous lecture, we see that for electric or in electrostatic case, force acting on the charged particle is equal to Q times E. So this is directly describing that the motion or the acceleration happen due to electrostatic force is equal with the direction of electric fields. Okay, so if the electric field is pointing to the positive Y direction, and then the signs of the Q itself is a positive one, then the value or the direction of the electric field is also the same with the direction of E. This is true for a certain moving particles influenced by external electric field. But if we replace the electric field with magnetic fields, the resulting force will be pointing to the different directions. It will produce a bunch of F, because the influence of B will be happening all time. Okay, so if we apply the external field at all time, so that B is interacting with the motion at all times. So the resulting F, firstly, it will produce upward condition, upward directions. But after the motion change from pointing to the positive X direction like this one, the force will be change. Okay, the force or the direction of the acceleration will also change. But the whole system, when the interaction becomes full, is actually pointing to a certain center, okay, to a certain center. So the difference between the influence of E and the influence of B to a charged particle can be seen here. The direction of F for an electric field is pointing to the same direction with the fields. However, for magnetic fields, the magnetic force will have a different direction with the magnetic field, where the magnetic force will be always perpendicular to the direction of B and also the motion of the moving particle. Okay, so this is a more clearer illustration. The electric force can do work on a charged particle, whereas the magnetic force cannot do work on the charged particle because the direction, okay, because the direction of F, the direction or the motion of F is not the same direction with E. Okay, so therefore, the work that is produced by F, since work itself is an integration of F with the path of the charged particle of the charged particle, and the motion itself will become a full circle like this one. So it's basically will goes to the initial point like this one. So from here, it moves here, moves here, moves here, moves here. And so since this is a closed path, okay, there will be no work done here because it initially starts here, and then the end point is also the same starting point. So therefore, there will be no changes in position. So the initial and the final the final and initial position of the force of the charged particle that we consider here is the same. So there will be no change in position, because so therefore there will be no work produced in this type of scenario when we have magnetic force acting on a moving charged particle, and it produces F over here. So the F itself moving like this one, the motion is circular. So it produces a circular path, a closed path, and it means that the initial position is the same with the final one. So therefore, there will be no work on this type of force. Okay. Okay, so here is a comparison between electric fields and magnetic fields. As I mentioned earlier, for magnetic field, if we have electric field that points upward, then F is also pointing upward. And this is true if the sign of the charge is positive. If the charge is negative, like an electron, then if we have an external magnetic force, external magnetic field pointing upward, then the force becomes downward. So therefore, the acceleration produced by the fields is upward for a positive charge, and it becomes negative and becomes downward if the charge is negative. For the case of electron, the sign of Q is negative. For proton is positive. For positive ions such as H plus, okay, H plus, okay. In chemistry, we have H2O for water, right? H2O is made of H plus ion and OH minus ions, right? So for positive ions such as H plus ions, the sign of the charged particle is positive, whereas for OH minus becomes minus. For neutron, okay, for any particle or any object that contains no charge, the value of Q or the sign of Q is 0. So in this case, whenever we have interaction between neutrons and electric fields, and even in interaction of neutron with magnetic field, there will be no force produced on the two cases. Okay, and then we also consider mass of electron, mass of protons, mass of ions, mass of negative ions itself will always be positive. Even for neutron, it still have its own mass and usually larger than the mass of an electron. And the comparison with the magnetic field in Lorentz law, okay, which is basically governing the magnetic force law, the condition that needs to be met is that the motion of Q or the movement of Q needs to be not in the same direction with B. So whatever the direction of Q with respect to the external magnetic fields must not be parallel or 180 degrees with the direction with B. So it needs to have a certain, so you need to have some degree of difference, okay, to B, to the direction of the magnetic field in order to produce magnetic force. Okay, so if Q is positive, okay, so in the scenario where Q is positive, V is pointing to the X direction, and then B is pointing to the positive Y direction, F will be pointing to the positive Z direction or the positive Z direction. If the particle is an electron or have negative signs, even though V is pointing to the positive X and B pointing to the positive Y direction, F will be pointing to the negative Z directions. Okay, so I think that is all for today's quick lecture on how magnetic fields is produced due to interaction of the charged particle with the external magnetic field, and the condition that needs to be met in the production of magnetic field itself. The charged particle needs to be moving. So if it's not moving, then V is equal to 0, then we will not produce any F. Okay, so as long as Q is moving into a certain direction and the direction itself is different with the direction of the external magnetic field, then the interaction between the motion and the external magnetic field will produce a magnetic force. And then later on, if the production is continuous, it's basically producing a circular motion like this one, and it will produce a certain radius of the motion that we could use for later applications. Talking about the application of this, we could see it in the cyclotron, we could see it in mass spectrometer, but we will discuss it in Thursday's section. Okay, so I guess that's it for today's quick lecture. We don't need to spend too much time because today is a holiday. Thank you if you follow the lecture from 10 a.m. today. We'll meet again on Thursday session as usual. Okay, I will stop the recording now.